I'm ready.
Yeah.
I think we can start now. I'm pretty sure more people will be coming in a couple of minutes.
Okay, that's fine.
I'll just give a short introduction. So
Sure.
this is our fourth keynote for the conference, and our speaker is Professor Somesh Jha. And so Somesh is a Luber professor in the computer science department at the University of Wisconsin. And his work focuses on analysis of security protocols, survivability analysis, intrusion detection, formal methods for security, and analyzing malicious code. And recently, he has focused his interest on privacy and adversarial machine learning. So he has published several articles in highly referred conferences and prominent journals, and has won numerous best paper and distinguished paper awards. So Professor Jha is a fellow of the ACM and IEEE. And today he's going to give us a talk on trustworthy machine learning, which I'm pretty sure will be very interesting. So thank you very much. The floor is yours.
Okay, thank you so much. So what I want to do today is sort of, I was telling, I don't know who was speaking, I forgot who was speaking. I said, you know, like CAV was the conference where I first published. And so, you know, it's very, I mean, that this community is very dear to me. And, but since then I moved to security, and now I made another shift, and I am mostly hanging out with machine learning folks. Mostly working on something called trustworthy machine learning. And I'll kind of try to sort of tell you what I mean by that. And the key takeaways from my talk, hopefully you can take it, is that, you know, we need sort of a security and formal analysis people to really enter this field. And this is happening quite a bit. There's a lot of, at least people who do analysis in security, privacy, and crypto are crossing over, but we need more of that. And, you know, we need more systematic and automatic ways of evaluating resilience of ML components. You know, we need, so for example, if you remember, there used to, I don't know whether they're still published. I saw the last CAP proceedings didn't have too many papers like that, but like analysis of security protocols, right? Used to be quite a hot topic at one time. And I think maybe what we need is a similar analysis of machine learning components. Okay? That's hopefully you can take away once I'm finished with the talk. These are the key takeaways hopefully you can take from the talk. And hopefully I'm going to make a better case of this than these two people made of that the election, the US election was a fraud. I don't know, the US people might get it, who these are, but others won't. So, I mean, we all know, I don't want to repeat this. A few years back, I had to kind of convince people that machine learning is being used everywhere. Well, I don't need to repeat that statement here. Now, our story begins in 2013. You might have seen stories coming out in popular press which said, hey, machine learning algorithm is essentially beating human performance in some tasks like object and face detection, breaking captchas, and so on and so forth, right? Hopefully you remember that. And, you know, there are a lot of doctors in my family, so this is kind of a slide for them. You know, they also were beating doctors in certain tasks like reading radiology readings and so on. But then what happened is people started realizing, hey, machine learning, when deployed in adversarial settings, has some very weird behavior. So for example, if you poison the Microsoft, one of the Microsoft chat bot with certain sort of well-chosen poison data, it starts tweeting out some sort of weird tweets, which actually, given the current situation, doesn't seem that weird, but at that time it was considered weird. You can do small changes to the content and kind of subvert the YouTube filtering system. Obviously, they're used a lot in autonomous cars and so on and so forth, right? Now, especially for this community, I don't have to say this, ML is also used a lot in safety critical systems, robotics, autonomous driving, drones, and so on and so forth. So obviously, robustness of components in that setting, I don't have to tell you that it is there. Now, this is a slide that I got from Sanjit Sesha. You can see the use of ML components in CPS systems is kind of on the rise here, right? So it's an important problem. So, by the way, whenever I say security, privacy, crypto mindset, I also am including people who do analysis techniques in this space, right? Static, dynamic analysis techniques, verification techniques. So don't think that I'm just talking about just security, privacy, crypto. In fact, if you look at our conferences, there are a lot of papers that are on formal analysis and so on. So I'm sort of including that in there. So this is a question that one of my ML colleagues asked me, and I was like, okay, what is different about security, privacy, crypto researchers than, let's say, ML researchers, right? So that got me thinking, and in general, this is kind of our blueprint by which we do analysis. Now, I want to say that every security paper doesn't have a formal analysis or proof in there, but in general, this is kind of our mindset by which we design things. So we have a system or a primitive sys. There is a security goal that we want to achieve. Threat model is generally what an attacker can do. So if you are doing security protocol analysis like Dolev-Yal, that is a threat model, right? And then we have some security assumption that some problem like factoring or discrete log is hard. The adversary cannot tamper with a protected memory or a trusted computing base, so on and so forth. And then a lot of our analysis boils down to that if the adversary, following the threat model, can violate the security goal, so for example, clobber the stack, then A must have violated a security assumption, right? So either A has to tamper with the TCB or in crypto was able to solve some hard problem, right? Like quadratic radiosity or sort of factoring or something like that. So, basically if the system if you can violate, the A can violate the system goal, then they have to violate the security assumption, okay? Now, how do systems get broken? People do very sometimes shoddy proofs and arguments. Well, that's why the threat model is too weak, or the security assumption is not valid because new set of attacks come up. So of particular interest is something like these brand new or ingenious attacks like power analysis, return programming, oriented programming, and so on. Well, then what happens is when these attacks come up, I have to go back and update my threat model and security assumption. Okay, so this attacks and fix cycle, like, you analyze the protocol or the system, you find attacks and you fix them and you go. This cycle is very, very important in the security, privacy, crypto community, right? In some sense, this is how the field moves, really, right? at least in our case, we don't take a system or protocol or primitive. If it is broken, we don't take it personally. In fact, if you look at current security and privacy literature, you will see a lot of papers that are kind of quote unquote attack papers, okay? Which is not true in other communities. For example, I remember when the Spectre meltdown attack came out on speculative execution, a lot of architects, I mean, computer architects, basically like, hey, this is some sort of a boutique attack. This is really not very practical, whatever, right? And now if you look at ISCA and other things, half the papers are on fixing some of these things. If you want to see how other communities react to it, I would also say, Google this, and I'll talk about this quite a bit. Google this phrase, insta-hide attack. Okay, so what I'm going to do is try to convince you that we need more of this security mindset, and which includes analysis techniques for security like fuzzing and formal verification and so on in trustworthy machine learning. And I will talk about that through the lens of two papers. The first paper, and again, these papers are just examples to make my point. If you don't understand something specific in that paper, don't fret about it too much. The first paper appeared in Oakland, which is IEEE Security. It's a short name for IEEE Security and Privacy Conference in 2021. And these are my amazing co-authors. There is a lot of interest in machine learning on learning from data, but in a private way that doesn't leak information. So think about learning from, let's say, medical data and so on, where you are not learning, you're not learning too much of the sensitive information about the patient and so on and so forth. So, this is our regular machine learning, right? You have a concept C, which is used to label your examples. You have a learning algorithm L, out comes a sort of a neural network or some model which tries to approximate this concept function C. And the idea is, can we make this private? Okay. So there is this whole field that is emerging in machine learning called instance encoding. And the idea here is that I encode my images or data set using an encoding algorithm E before I run my learning algorithm. And if my encoding algorithm is somehow obfuscating the private features, then by definition, I'm not learning the private features, right? So for example, in tabular data, suppose my encoding algorithm is randomizing a lot of the sensitive information, and I can still do my learning well, then by definition, I'm not learning private information, right? So this encoding is I'm learning over that, and that's what's making the algorithm private. So the benefits here, if this was possible, the benefits here are the encodings do not reveal any information about the inputs, and the computation can be done in encodings, and you can use this in multi-party settings like healthcare, where privacy is important. And again, it's very important to know that algorithm is run on encoded data, okay? And so the final model is as private as the encoding. By the way, if you have questions, you can just unmute yourself and ask. I don't mind that, by the way. You don't have to wait to the end. There was an instance encoding that was developed by researchers at Princeton called insta-hide, which was at ICML 2020. And Sanjeev Arora was one of the co-authors, and it won the Bell Labs Prize. It was the second position in the Bell Labs Prize. And so we started looking at this scheme, and we were able to break it. Okay, so we in this paper, which appeared in Oakland, we tackled these two questions. Is InstaHide, the instance encoding scheme developed by Princeton folks, is that private? And can anything like InstaHide be private? Okay? And we will answer both these questions in the next few slides. The InstaHide algorithm is kind of quite clever. What it basically does is take sort of some private data and some public data. Maybe you scrape the public data from Instagram or whatever, Facebook or something, and it randomly combines them. And this is not their stuff. This is an old algorithm in machine learning called mix-up. Okay, so think about this as it kind of randomly mixes the images from private and public thing. So you get some random image here, right? It's kind of a mixed up version of these 4 images. Then what it does is it randomly flips the pixels. Okay, the sign of the pixels it randomly splits, and that's your InstaHide algorithm. And then they learn on these obfuscated images. So remember, what the operations that happened to encode this was mixing 4 images together and then random side flipping. And they show that they can get very good accuracy even if they learn on these encoded images, which seems very interesting, right? They got pretty good accuracy. The accuracy drop from just learning on the image, the regular images was very small. Okay, so this is an algorithm. So I give you the specification of this InstaHide algorithm, and I say, hey, is this really private? And we designed an attack for it. And the intuition here was very interesting. The idea was that if you are able to learn from these encoded images, then they must be keeping some signal of the old image, otherwise you won't be able to learn. So what we essentially do is have some sophisticated clustering algorithm on some embedding of these, and encodings of the same image cluster kind of together, and using that we were able to recover the original image. Okay, so these were the original image, and these is what we extracted from the encoding. So the answer to the first question is no. And then what we did is we tried to see that is there a similar scheme like InstaHide that can be private? Maybe InstaHide got unlucky, but maybe there is a similar scheme that might be. And then we have some impossibility results there. And this is very similar to, if people have studied crypto, this is very similar to the semantic security game in crypto. The idea is that I give you 2 dog images, I encode them, let's say using InstaHide, and I give you one of the encodings. And you're supposed to tell whether that encoding belongs to this white dog or black dog. Now you can imagine, right? If the encoding was really very good, then you should not be able to do much better than random guessing here. And we show that that's not true. What we show formally is that if the learning algorithm, remember there are 2 components now. E is the encoding scheme like InstaHide, L is your learning algorithm. What we prove in the paper is that if your learning protocol achieves better than random accuracy, half plus epsilon, on 2 concept classes. So think about these 2 concept classes as one concept says whether it's a dog, and the second concept says that what the color is, white or black. If that is true, then there is a polynomial time adversary that can break our indistinguishability game with better than random probability. Okay, so that means it can tell between the 2 images with better than random, and that generally means it's sort of broken. Okay, and the second one generalizes this to So sort of like which depends on the data size n, which I will not get into. So we basically, InstaHide guys put out a challenge. We sort of broke them. And the idea here is, and this is where I think people in the audience will be interested. Well, does this really invalidate the InstaHide security claims? Well, they didn't have a formal falsifiable claim of security, right? It's basically, if I give you a scheme and I don't formally specify what is the correctness criteria for that scheme, then what does it? I can by definition not falsify. So that's what happened. Now I want you to keep an eye on this. This attack was extremely innovative, and the lead there was Nicholas Carlini. Well, are you going to, if I give you a new scheme like InstaHide, are you going to again rely on Nicholas Carlini to break it? Or is there a formal analysis, sort of a systematic way to evaluate these proposals to see whether they're secure or not? Okay, so that's where the ATVA community can really sort of contribute, right? What are we good at? I mean, a lot of our analysis thing, what we're good at is coming up with algorithms that generalize to a lot of different kind of things, right? So that's where I would need, I mean, we don't want to, again, now, by the way, there's these new schemes being proposed all the time. And there was another one called NeuraCrypt, okay, which we also proved was not private. By the way, any questions so far? Otherwise, I'll move into NeuraCrypt. If there are any questions, please, I don't mind if you unmute and just ask me.
Yeah, I think it's all good.
Okay. So there is another instance encoding scheme called NeuraCrypt, which was sort of proposed. This was another instance encoding scheme where there's a labeled data set. And here there was a key, sort of key there. It was a keyed encoding scheme. And you get an encoded data set and you learn from that, and they were able to do quite well. Okay. So the difference between this instance encoding scheme and the InstaHide was here there was a key. Okay. And these are the authors. I think they had submitted it to NeurIPS. I don't know whether the paper got in or not. Maybe somebody can check it. By the way, one thing I do want you to understand, hopefully you saw the author list of both InstaHide and NeuraCrypt, right? These are not lightweight people, right? I mean, these are some very well-respected researchers, and they were able to come up with a scheme which was not secure. So this proves to me that we need like a formal analysis technique here, so that if let's say one of my students comes up with a technique saying, hey, I have an instance encoding or a privacy preserving machine learning technique, they can give me a specification of the neural network algorithm or the learning and encoding algorithm, and I can do some analysis to tell them, no, this is not private. Because you can't be just putting out papers and then waiting for teams to break your scheme. So I just wanted to kind of sort of give you this, that this is not like this entire team was from MIT, and like Manya Gobadi, Tommy Yakola, Vinod, Venkatranathan, Regina, and Muriel. These are all top-notch sort of folks. So this seems to me ripe for sort of some formal definitions, analysis, and so on. So how does roughly NeuraCrypt work? So the key generation here is basically sample a neural network with random weights. And then essentially the encoding is some sort of embedding that this neural network generates. That's your encoding. And they have a privacy definition which basically says that if I give you two cat images, the distribution that you will generate, because remember this key is random, the true distribution for these two cat images are going to be quote unquote indistinguishable. The threat model here is that adversary sees the plain text and its encoded version and must not learn any information beyond the labels. Okay. The authors do a security analysis of a perfect scheme, and then they have an instance of that scheme which they call NeuroCrypt. Okay. I'm not going to go into that. I'm sort of glossing over a lot of details here. Now, they also put together a challenge. They gave 10,000 images and their encoding, and the idea was, can you match them? Can you say, hey, this encoding corresponds to that dog, this encoding corresponds to this, and so on. The second challenge was they give an encoded data set, and you're supposed to come up with another key K prime that approximates key K. And we sort of argue in our paper where we break NeuroCrypt that this challenge 2 is not realistic. Short story, long story short, we broke NeuroCrypt. Okay. And our attack, basically high-level idea is that we use statistical invariances in different layers of a random neural network. Okay. In some sense, this goes back to our last intuition that if your encoding is keeping enough signal to generate good encodings, then it must be learning something about the data set. Our step 1 is we train an embedding. Then we use embedding to calculate the similarity between encoded images. Okay. And then step 3 is to, kind of use these similarity metrics to kind of mix and match. It seems like a very similar to sort of a bipartite matching problem. Okay. Now, what about challenge 2, where we are supposed to actually almost do a key recovery attack, right? We are supposed to find a key K, and this seems to be kind of inconsistent with the threat model of NeuroCrypt. And so we didn't do challenge 2. You can read our paper for it. I mean, I'll give you an idea, right? Suppose I do an encoding, which is basically the image and a pseudo-random function that depends on X and K. Okay. This is provably secure in challenge 2, but it is useless because I'm revealing the image in plain text. So the idea is there are a lot of these little things that basically what we have in our paper is that challenge 2 is kind of not realistic. Okay. Now, again, what we have next is we try to say, can any encoding approximate this kind of ideal encoding? Now, notice that our previous algorithm or result from Oakland didn't apply because this is a keyed encoding and InstaHide was not a keyed encoding. Okay. So here our result is very interesting. What it says is that if your encoding scheme gives you very good accuracy, then I can already extract the concept function, like the labeling function that you use to label the images from the encoding itself. So then what's use of learning, right? So that's what our theorem basically says. And the proof idea is very similar. And essentially we sample a lot of keys to get different encodings. And then we use boosting for the classifier. So it's a clever algorithm. So summary, NeuroCrypt is not private in the proposed threat model, and challenge 2 is not relevant to privacy. Okay, now let us recap what happened, right? Here are 2 very good top-notch groups came out with an instance encoding algorithm for privacy-preserving machine learning, which we broke. I can see when I was bidding for papers in in one of the ML conference, I could see that there were a lot of um, papers being submitted in this thing, okay? And I'm assuming some of them will get in. Are we going to rely on humans to keep breaking these things? Okay, or are we going to have a systematic formal analysis kind of technique where if I give you a specification of an encoding scheme and so on, you can try to find these attacks automatically. Okay, you know, so that's where the ATVA community can come together, right? So this is what I mean. ML needs more security and sort of this analysis and crypto mindset. Most defenses and schemes get broken very quickly. So for example, you can see the two papers that I just covered. Now, if you want to understand the mindset difference between a security crypto person and a non-security crypto person, please click on this blog article. This is by Sanjeev Arora. And you can see that there is a lot, I think it's a mindset difference. It's not just a difference between, it's really a very adversarial mindset. We need that. Now, instant encoding is not an isolated case. There are many informal ML security notions like model watermarking, resilience to model theft, robustness to black box attacks, resistance to inferences. And here also we need people who have formal analysis background to come in and try to evaluate these things. Right now, the entire community depends on very few people to just break these schemes, right? I mean, it's something like this, right? If in security, in software analysis and software verification, if you only required on humans to find bugs and problems, that's where we are right now with this. So we need really people from this community to jump in and help us here. Now, many ML security projects are releasing challenges like InstaHide and so on and so forth. But what is the goal of a security challenge? Okay, a challenge should not substitute a formal security claim, right? You should publish a challenge, but the challenge design goal is that if you solve the challenge, it falsifies the system's security claim, but the opposite is not true, right? The converse is not true. A challenge is not enough to give you a system security claim. You need a formal definition, a proof, and so on and so forth. Let me give you an example. This is the formal definition of what it means for an RSA scheme to be what is called CCA secure, which is chosen ciphertext attack secure. And basically, what you do here is, people who are not familiar with crypto, is the first step, you generate a public key, private key. Then the adversary generates two messages, M0, M1, and ignore the state for now. And the encryption scheme flips a coin, B, in the third step, encrypts one of the messages, and then asks adversary to guess which message was encrypted. And a lot of these schemes say that your CCA is secure if for all probabilistic polynomial time adversaries, the probability of winning this game is negligible. Now, Jill Barth, who's, I think, where is Jill Barth now? Is he at Bochum? I think he might be at Bochum now. He has done a lot of work on having formal proof systems for such kind of crypto definitions. like easy crypt and so on. So there's a lot of people from the formal analysis community who have developed tools to sort of mechanize these proofs, right? Now, this proof, if I give you a security challenge, you cannot, that is not a proof that it is CCA secure, right? Because there is a universal quantifier sitting there. For all PPTA adversaries, the challenge is negligible. So all it's basically saying is that just because if I give you a secure factoring challenge and nobody is able to solve it, doesn't mean RSA is CCA secure. Okay. I mean, I'll give you sort of, this sort of the Zodiac cipher with cryptanalysis for 50 years. But is it a secure encryption scheme? Most crypto people will say no, okay? Because it doesn't satisfy any of the modern notions of crypto. So, I'm a little bit ahead of time. And here, what we need is, we don't want to keep getting these schemes, people coming up with these schemes like InstaHide, and so on and so forth, and then relying on other groups to find attacks. We want formal proof analysis techniques, proof systems where, let's say somebody gives you a specification of these encoding schemes, I'm able to find these attacks automatically, or find them sort of like, at least in some semi-automatic way. Any questions on that? Because I think this is where we would need a lot of help from the ATVA community. Any questions so far? Or comments? I'm open to comments as well. Anything?
I have a question.
Okay. Can you,
Um,
I can't see everybody. Can you say your name?
I enable my video feed. You should be able to see me, I think.
Oh,
Yeah.
okay. Yeah, I can see it.
Yeah, I'm Alan Tu. I'm from the Australian National University.
Yes.
So this is very interesting talk. Thanks for highlighting all these issues of security of machine learning. I guess my question is, I mean, I know a bit about crypto, very little, but
So I'm assuming you know about this easy crypt system that Jill and all.
Yes. Yeah, I've played a bit with that. So I guess my question is, I mean, crypto, when we formulate notions of security, is usually an encryption scheme, for example, is secure if you can't learn absolutely anything about the ciphertext, right? But the machine learning, through this encoding, it's still able to learn something, as you pointed out in one of the slides. So that means that you can actually figure out relationship between the ciphertext, and that probably already breaks a lot of assumptions about security.
Yeah, but maybe there is a weaker notion of security and privacy here, right? So let me say this, that these schemes, InstaHide and so on, are more closer to symmetric crypto to me than public key crypto, like AES and so on and so forth. Okay. Because I'll tell you why. So if you look at AES, right? So there isn't a formal proof that AES is a PRF. It's basically what, when NSA NSA evaluates these things, what they do is they run the best attacks like differential crypto analysis and so on, and say, oh, these things withstand it. Okay. So to me, this will be more similar to those schemes rather than public key crypto schemes like RSA, lattice-based crypto, and so on. Does that make sense?
I guess I wasn't very specific on whether it's symmetric or public key, but generally a requirement on security on encryption scheme is that there should be no information leakage about the plain text at all.
Well, it is not all the time true, right? For example, if you look at a linear homomorphic scheme, it allows you to do linear operations on the ciphertext.
That's true. Yes, yes.
And if you look at some order preserving schemes, so order preserving encryption schemes, then I can tell the order. So there are encryption schemes where they allow you to do some operation on it.
Right. So you are still allowed to infer relationship between ciphertext, but just not between ciphertext and a plain text or ciphertext.
Exactly. But in this case, obviously, it was broken, right? Yeah. Now, I will tell you where I think there can be a lot of synergy with this community is the following, right? And by the way, I have seen, I have always wondered why the formal methods community hasn't picked up on it. So if you look at analysis of symmetric crypto schemes, this goes back to probably before some of the attendees were born. Adi Shamir had this thing that he did with Eli Biham called differential cryptanalysis, which basically was that there was a lot of these one-off attacks that were using somehow that the some of these rounds were behaving like linear functions. And they were able to use that to do something called, come up with a framework called a differential cryptanalysis. And I have always wondered why can that be made into almost like a tool? I mean, differential cryptanalysis is like an algorithm. If I give you something like AES or something else, now it becomes almost like a model checking problem that does there exist an attack in this framework that violates this AES? So I will tell you where I think there is a lot of room here is that can you take some of the attacks that what we have developed here and come up with a formal framework informed by these attacks, which will not prove that there is no other attack, but you can say, hey, I can prove that there is no attack of this type here. Because right now, the problem in machine learning, I think you will agree, is that people are publishing faster than people can evaluate. And so, but I think this is a very ripe for somebody in formal analysis to come in. Did I answer your question or?
Oh, yeah. I think you answered it very well. Thank you.
No problem. Now, the other thing is where also analysis people can help is right now in machine learning, adversarial machine learning, the way people are evaluating robustness is, oh, I run some existing attacks and my model's robustness seems very good. Well, then you know what happens there is somebody looks at it, says, oh, but I can tweak, if I know that your defense works like this, I can kind of tweak my attack to now go under. So you'll be surprised to know that one of the ICML papers 2-3 years back broke almost all defenses that appeared at the previous ICLR. Okay. Now, is there a more systematic way to evaluate machine learning models? Okay. And we know that hiding the defense from an attacker is not a good strategy, right? As one of my co-authors said, the attackers can also access archive just like us, right? I mean, it's not, they also have web access. And there's a lot of older fields that I see that a lot of ideas that were discredited in other fields have started coming up in new guises without knowing that those things were all discredited. So I think that is something that I will end with is that we need more people from this kind of a community to come in and sort of systematize some of these evaluation algorithms for this field. And that's kind of where I'll end. And I just want to say that, I would really encourage some people in this field to do that, because this is a huge opportunity, because everybody I talk to is interested in privacy preserving machine learning. A lot of algorithms, protocols coming up in this field, and who knows whether how much of it is secure and not secure, and are we going to just rely on humans to vet all of them? So on that, I will end, and I will open up for questions. And again, I'll be here till whatever time. I mean, I enjoy discussing stuff with folks. So if you have any more questions or so on about my talk, and I'll obviously make these slides available.
Hi, Somesh. This is Vijay here.
Hi, Vijay.
Sorry, I was a little bit late.
No problem.
You mentioned something about formal definitions and
Yes.
the need for it. What about differential privacy, which has become a kind of a buzzword in machine learning, right? And I was wondering whether that.
Yeah.
Go ahead.
Yes. So that is a very good question. So I'll tell you what happens. So the way to train differentially private models is something called DPSGD, which is basically a differentially private version of SGD. Okay, stochastic gradient descent. If that worked, we would not be here.
I see. Yeah.
All these things like insta-hide and all that, they're trying to come up with these algorithms, because the accuracy drop for DPSGD is too much. It's around 25-26% over the normal accuracy.
Right.
So, and for most complicated things, that makes it useless, right? So if you think like CFOR 10 or something, and your accuracy is 94%, now I say, oh, you only have 71%.
Right.
So all these things, all these algorithms like DPS, insta-hide, all that stuff would not exist if DPSGD could give you good accuracy.
Yeah.
Obviously, the differentially private people don't like that. But it basically doesn't work in practice. On small data sets like MNIST or whatever, sure, but MNIST is good for class projects, basically.
Right.
Does it make sense?
Yeah, totally. Yeah.
So people are trying to think outside the box, so to speak, and come up with privacy preserving machine learning algorithms like insta-hide and so on, because they, DPSGD just has too much of an accuracy drop.
Yeah.
Did I answer your question okay? Or
yes, Somesh, you did. Totally.
Okay. Obviously, the differential privacy crowd doesn't like to hear that, but that's where it is.
Yeah. Yeah.
Any other questions?
So yeah, I had one more question, and I missed a couple of the early slides.
Yes.
So is there a total, like outside of DPSGD and insta-hide that you mentioned, is insta-hide from Princeton, or is it?
Yeah. Insta-hide is from Sanjeev Aroda's group.
Okay.
And NeuroCrypt is mostly from, it looks like Tommy Yokola, Regina Barsley, and that group.
Okay. Outside of these three efforts, there are no other.
Oh, no,
big
I'm seeing a lot
that you're aware of. Okay.
A very simple Google search, and while I was bidding a for NeurIPS reviews, I could see a lot of submissions.
I see.
Because think about it this way, right? If you could come up with something that sort of works and doesn't have that big accuracy drop that DPSGD, the number of banks and healthcare people that care about this, you could be printing money, basically.
Right. Totally.
So there's a huge interest in privacy preserving machine learning.
Yeah. Now, is a formal analysis for non-privacy attacks, like, for example, adversarial attacks? So one could argue that adversarial is not technically a privacy oriented property, if you will, right? Or adversarial robustness. For that, I'm assuming you would require a different standard and a different way of arguing how, why your defense is effective. And I wonder, I mean, I think you're alluding to the fact that arguments from crypto could be lifted in this setting, but nobody has successfully managed to do so.
I mean, there is this whole community, right, that is doing verification of machine learning algorithms, verifying the robustness of machine learning algorithms. I think even CAV has a competition on it or something. But the problem is,
trouble. Yeah,
well, I'll tell you what the trouble is. So Zico Coulter's from CMU, they won it this year.
Right.
And by his own admission, they are like generations behind what people are using now. They can verify maybe, I don't know, small neural networks. People are already in Google and OpenAI talking about billion parameters neural networks.
Exactly. And the other issue with the verification crowd is that the way the adversarial robustness property is specified is like, this LP ball around the various pixels, right? And the problem with that is that you can go out of the, there's a trade-off now between the difficulty of verification versus how large the LP ball can be.
Yeah, but even if
so you can actually.
Yeah, go ahead.
So the point is that the trouble with verification is, even if you give me a certificate saying it is verified with respect to this LP ball property, you can still attack it because there are sophisticated testing methods that are out there that can still find
there is. So for example, I can, if you very simply just blur an image a little bit, right? The LP norm, in LP norm, it's a huge problem, right?
Correct. Yeah.
But so if you verify there, so that is my little bit pet peeve with the verification community, to be honest. I don't know, is that at least in that space, we are 5 or 6 generations behind. So even if you can verify and the kind of stuff that is, I forget the name of the competition. They have a competition as well.
VNLib.
Is it? So I mean, those things are never you. I mean, these things are just come up for the competition. They are not useful. I hope nobody who participated in the competition is listening.
This is recorded and put on YouTube. So
because so I think that's the problem. I think the thing is we are a generation behind a little bit.
Yeah, totally.
And in the ML guys are making models bigger and bigger and bigger. And our verification competitions are just simple.
And the testing tools are so much more sophisticated these days. Like
exactly.
They're able to. So.
Well, I don't know. I find that maybe a better goal. So if you think about it, right? Something like symbolic execution and so on, concolic execution, has had a lot of impact in the software community, but it still uses under the hood a lot of the stuff that the verification community has developed, like Z3 and so on.
Correct. That's right.
So I have wondered whether there is a concolic, like symbolic execution style thing that might be more useful here. Sort of like saying,
there are tools already doing that.
Oh, there are tools already doing that. Okay.
Yeah. So I've been following the testing community for some time, and they are miles ahead of the verification community in terms of the size of the models they can attack and in terms of the properties they can attack.
Yeah, but again, the
And they are
problem
using
is,
symbolic.
I will tell you,
Yeah.
Dave, why they are a little behind the testing community. They're still looking at LP norm attacks, aren't they?
Not necessarily. So there are papers out there. I mean, I have one paper where you can actually specify a property and then attack with respect to that property. So you can find counter examples. You can find counter examples. So people are looking at these kind of attack methods, and these attack methods scale, maybe 1000x over the verification methods.
Yeah. But I'll tell you the other problem, right? So the problem is that at least from what I'm talking to a lot of the companies, this problem of privacy preserving machine learning is a much bigger problem than robust machine learning.
Yeah.
They care more about this because, yeah, you put a patch on a cat and it becomes a dog or whatever.
Right.
They really, they don't consider that as a imminent danger, so to speak.
That's right.
But this is something they really care about now.
Yeah.
They care about right now.
So this is a call to, yeah. So, I mean, I think, so it's kind of a call to action as well. And you could think of people doing a line of research where they really don't care about formal guarantees, but maybe in a practical setting, more practical way, at least some of the attacks can be thwarted or their effects can be minimized.
Exactly. Or you can say, hey, I did some testing and these sort of attacks are not possible in your algorithm. So you at least get some assurance. Right?
Yep, totally.
But I really do think that one thing that I sort of, this is more a call to the community here, is that if you want to make impact on a field, like in this case, privacy machine learning, it is not enough to be out, you have to be embedded inside the community. Okay? Like you have to publish, you have to go to ICML, you have to go to NeurIPS, and also go to verification engines. What I find is, in a lot of cases, there is a big knowledge impedance mismatch. Like the ML people don't understand what the testing and verification people are doing. And the verification testing people don't understand how fast the field is moving.
Yeah.
So I think in order to make impact, Vijay, you have to have somebody or a group that straddles the two.
Yeah.
It is that whole style that, oh, I take an ML algorithm, I throw across the fence to some verification testing folks, and they give me the results back. I think that is not going to be super effective.
Yeah, agreed. Yep. Now I think those are very, very good, wise words.
I mean, this goes back when I was working with Ed, he was very, very adamant that we go and see how hardware engineers work.
Yeah.
Okay. It is not enough to say, okay, I have a tool here, Intel folks, let's use it. He spent a lot of effort actually talking to them, working with them, so that they know exactly, okay, this is what is going to fly here, right? So
yeah, totally.
I think that's very useful. Because I see
and that's a model,
like, at least in verification and analysis, there is this thing, okay, I'm going to sit in my CAV, FSC, ICSI, PLDI, POPL bubble, never go to an ML conference and write about ML.
Right. Agreed. Yeah, I think.
Sorry.
Are there additional questions? Jing, did you have any questions? Sorry, there was somebody speaking. Go ahead.
Just
Oh, yeah.
want to ask, or maybe a remark or a comment. So what's happening on the system side? We know that for a long time we have things like Intel SGX, Secure Enclave, right?
Mhm.
And if you use any of these, then you don't actually have to worry about all this sophisticated privacy preserving and encoding. Just dump
This is
everything on the Secure Enclave and you're
This
done.
is a very interesting question. So, at least from what I can tell, you should look at this paper. I'm going to put on Slack. Oh, not Slack, sorry, chat. I'm using Slack too much. There is a paper that appeared in ICLR called Slalom, which is from Dan Bonnet's group at Stanford. So at least at this point, the secure execution environments are not even good enough that they can run inference on models. So you really do need a GPU. Okay. So they cannot forget training. They are not even able to do inferencing on models. So this paper is very interesting. And when you might look at it, is basically saying, okay, I want to offload some of the computation to GPU from the trusted execution environment, but I don't trust the GPU. How do you do that securely? Okay, but they don't even do training. This is just inferencing, and they're still much slower than the other GPUs. So the short answer is I don't think trusted execution environment can even do inferencing right now for moderate size models. Forget training. Does it answer your question or no?
Yeah, so like I said, I was more curious about what's the developments in this area. I guess improving hardware is probably easier than coming up with some really secure encoding. I don't know. So what's your perspective on that? Yeah.
But you would need like a secure GPU cluster, basically. Not just like a trusted execution environment.
Yeah.
I can't even run a logistic regression inside there. I think it's too slow. By the way, this is again, one thing I find is that there is a lot of these crypto papers written by crypto people, like Slalom, like which I put here. Now their proofs are all hand proofs, right? I mean, these are like, you know, like, oh, lemma theorem. It would, I think it'll be good to have, I mean, I'm pretty sure a lot of their proofs can be mechanized.
Yeah, I mean, there's now a community just doing crypto proofs.
Yeah,
major
like
peer improvers support crypto proofs already.
exactly, but you know what happens, Ivan? One thing that is my pet peeve is that these tools never get updated. Like for example, with EasyCrypt right now, it lacks a lot of theories because you know Jill is doing some other things now. I mean, he's interested in some other things. He's not doing that. So these tools have to live and breathe, and new theories have to be added to them to support these kind of things. And that's my biggest thing. I mean, you know, these things are just like this is why I give Z3 guys a lot of credit, right? I mean, they are constantly updating and so on. A lot of these
a lot more people working on it.
they have a lot.
A lot
The
more
problem is
funding.
like I think there was one student of mine who was trying to use EasyCrypt for actually verifying a protocol that looked very much like Slalom. It lacked a lot of the stuff that we needed.
I think Somesh, this aspect of mechanizing the proof, we are probably one step removed at this stage, right? Even kind of what is the right kind of argument to make, even a paper pencil argument for a privacy preserving defense mechanism. I think we still don't have an agreement on that. Whereas in the formal methods community, we had more than 30, 40 years of discussion and work on that before mechanization became a thing.
Yeah, I mean, so I think one thing that I really like the direction, and this is something that, I don't know, maybe you can invite him in the next ATVA.
Mhm.
People are trying to now do co-design of ML algorithms
Yeah, right.
that makes verification easier. Okay, so let me give you, before we end, let me give you one example. So do you guys remember that paper from David Dill and Clark Barrett and all that, which was a few years back in CAB on verifying neural networks, right? Basically ReLU networks.
Mhm.
I forget what was the name of the paper.
Reluplex.
ReLUplex, yes. And I think they won the best paper award at CAB or something like that. Now, obviously, if I gave you a neural network where very few ReLUs are activated, so I bias my ML algorithm to activate very few ReLUs. Their algorithm, verification algorithm, can verify it faster.
Right.
So Alex Madhuri in one of his postdocs, I think his name is Eric Wong or something. I think yeah, WONG, are looking, saying, can we, when we train ML algorithms, can we bias it towards sparse activations?
Yeah.
And their motivation is that then downstream verification algorithms are going to get faster.
Yeah, and
That is a very promising direction. Can we architect machine learning algorithms where maybe you can do compositionality and so on and so forth, and rather than, hey, I train my OpenAI BERT model with billion parameters and throw you across the sort of the wall and say, okay, verify this.
right.
Well,
There is some effort in the space of binarized neural networks as well, which one could argue are more amenable to analysis.
no, but these
right? So
guys,
a few,
they are specifically looking at this problem where what they want to do is they
right.
want to speed up the downstream verification algorithm.
So one final question is,
Yeah.
you can think of machine learning training as a form of synthesis, really, right? Because you are trying to find these holes in your
The soft synthesis, not.
It's a very kind of soft form of synthesis. There is no, and I wonder if there is a way to modify the training process so that you can get guarantees. Is that a possibility? By, in some sense, correct by construction.
Yeah,
And
but
I know
when
that.
when you're optimizing, right? What would you do? Like
So
we don't even understand whether SGD can find global optima or not.
no, true, but people have looked at, is it possible to reduce the machine learning training process to a solver call? So at the end of the day, you are solving an optimization problem. So you could technically solve it using a solver call, which is a different take, completely different take relative to using SGD. But the problem, of course, is scalability, because
Yeah,
solvers cannot scale like SGD
exactly.
can. So
I mean,
anyway, yeah, people are thinking in these directions,
but interesting. I mean, the thing is that, look, we don't even understand the dynamics of SGD and Atom and so on, right?
yeah, that's fair.
So, okay,
Awesome.
it was great interacting with my old home crowd, as I said, and it's hopefully next time I will see you guys in person.
Awesome. You mentioned you're going to post the slides.
I can send it to I can dump it to PDF and send it to you guys, or put it in some link and.
Yeah, you can send it to me and Jay, the
Okay.
co-organizers. Yeah.
Okay, thank you so much.
All right. Thanks, Somesh.
No problem.
Thanks very
Bye-bye.
much for giving me keynote. It's fantastic.
Yeah.
See ya.
Thank you so
Great.
much.
Thank you. Bye-bye.
Bye.
Yeah. Okay, so our next session is session 7, and it's going to start at 10:30 in Brisbane. So in about 15 minutes. So let's have a little break, have a cup of tea, and we'll come back in 15 minutes.
Hello, welcome to section 7 of the presentation. So in this section, we have 3 papers to be presented. May I just call upon the 3 speakers who will be presenting the papers? Are they all here?
Hello. Hello,
Okay.
my name is
Right.
Armando. I will be presenting the paper on Pineapple.
Oh, yeah. And second Oh, second presentation of verified code is also here. Presenter here. Not yet, maybe. Anyway, we'll go as planned. We'll go with first paper on PyNever, a framework for learning and verification of neural networks. I'll pass on to you with the first presentation.
Okay. Thanks. I'm trying to share my screen.
Yeah, I'll make a co-host. So, yeah, that's
Okay.
good.
You are seeing the presentation, right?
Yeah, we have.
Okay. Okay, so thanks for hosting our paper and presentation. My name is Armando Tacchella, and this is a joint work with my colleague Luca Pulina and my student Dario Guidotti. So we all know that neural networks enjoy many successful applications in several fields, including natural language processing, computer vision, cooperative agents. And there are a lot of success stories about the usage of neural networks, specifically modern neural networks like convolutional networks, deep networks in these fields. And we also know that neural networks are known to be prone to some kind of attacks that make the result kind of fuzzy in some cases. So for instance, in case of convolutional neural networks, it is known that adding some noise, which is not even perceivable by the human eye, the classification of a neural network may change dramatically. For example, in this case, from panda to gibbon. Formal verification is one of the techniques that can help find out these issues and possibly correct them. Of course, there are other approaches, more statistical in nature, that are originated mostly from the machine learning community, but formal verification presents some interesting results, especially and application, especially when it comes to safety or security critical applications where you need to guarantee that your software respects certain properties. So in the recent years, since 2017, I would say there's been quite an impressive development in neural network verification. There are now yearly competition for software that solves the problem of verification of neural networks. And there are also some interesting success stories for applications, as I said, in safety and security critical areas. However, if we look at state-of-the-art neural networks, those that get employed in actual applications, I would have to say that those networks are still very hard, if not impossible, to verify. Okay, networks with millions of nodes currently escape the realm of very formal verification techniques, at least those that we are interested in. So having smaller networks to verify, or some kind of abstraction techniques, is desirable in order to be able to attack these problems. Of course, it is infeasible to prove a property by running neural networks on all inputs. So we cannot go by testing a network on all the possible input. One potential approach to get to verify networks is to use abstract interpretation. So abstract interpretation, as we know, provides a finite approximation for potentially infinite set of behaviors. And in fact, our methodology in PyNever leverages abstract interpretation to verify neural networks. So our goal is to try to manage verification of neural networks by providing abstract interpretation techniques. The idea is fairly simple. So the concrete input set consists of input patterns, input data points. Here I'm showing a simple example in a two-dimensional space. Each red dot is a data point. Now you can abstract the input set as a box. And in this case, you would say that the input dots lie in a certain range on the X and Y axis, or you can use more refined abstractions like polytopes or others. In our case, we use polytopes. And once you consider an abstract input, you can, in principle, analyze the behavior of the neural networks on the whole input set, not just on single points. So, but now, once you have abstracted the input set, say you have a neuron like this in a picture, an activation function like this in the picture. This is a rectified linear unit, or ReLU. ReLU neurons zero all the inputs on the negative side and perform an identity function on the inputs on the positive side. The function is non-linear overall, but it is linear in the two parts. And the idea is, once you get a polytope as the input to a couple of neurons, in this case we are in 2 dimensions, then you will get this kind of output. But the point is, how do you process this abstract input to this abstract output? And the point is, you need some kind of abstraction also for the transformer. And we call this abstract transformer. So once you have your abstraction of the input and your abstract transformers for all the stages of the neural network, then you can compute an abstract output. And once you have the abstract output set, then you'll have possibly some safe region identified by the requirements that you give to your neural network. And now you have to check that the abstract output set does not intersect the unsafe region, okay? Which here I wrote as the negation of the safe region. So the neural network is safe if the abstract output does not match any point in the unsafe region. And once you have the abstract output in the form of a set of points, then you can perform this computation. The point is, it's an abstraction, so it's an over-approximation, meaning that it is possible that you will say that your abstract output intersect the unsafe region, even if the concrete data points would not. So in fact, you may declare that your abstract neural network is not safe, while the neural network, the original neural network, is in fact safe. In this case, so if you have spurious counterexamples, it means that your abstraction is too coarse and you need to refine it in some way. Okay, so in PyNever, this is the technique behind PyNever, and to support abstraction, we use star sets. A star set is specified as in this definition, so is a set of points that respects this set of equations, where V is called a matrix of basic vectors, and C is called center of the star set, and the vectors X should respect a set of predicates. In general, star sets are a very powerful representation because this set of predicates is just arbitrary. But in our case, the set of predicates is a set of linear inequations, meaning that in our case, we use star sets to represent polytopes, okay? If you define a star set in this way, so the predicate is just a set of linear inequations, you can prove that you can represent polytopes, and in fact, only polytopes, exactly polytopes. It is easy to perform an affine mapping of a star set because you just need to apply the mapping to the basis vectors and the center. So in fact, the good thing about star sets is that fine mappings are easy to compute, and inside neural networks there are a lot of such mappings, because each time you input your stage to another one, you undergo such transformation. And once you have performed this transformation, you need to handle activation functions. And in the case of ReLUs, which are by far the most common activation function in current neural networks, you can go with two approaches. Either a complete approach, so no abstraction whatsoever, or an approximation algorithm, which involves some abstraction. So if you don't abstract for each neuron that you input your abstract input to, then you'll have to split each input star in two stars, one for the lower part of the ReLU and the other one for the upper part of the ReLU, as shown in the picture. This means that for each neuron, if you have one star as input, you get two stars as output, and this happens for each neuron of the network. In the worst case, this means that for each unstable ReLU, you have an exponential blow up. You trigger an exponential blow up, because for each unstable ReLU, you get two stars. And so as many unstable ReLUs are there in the network, the more unstable ReLUs are there in the network, the more the blow up is evident. If you have lots of stable ReLUs in the network, you can still hope to run a complete algorithm, because you won't have this split for most neurons. But if most neurons are unstable in the network, then you'll have this split, and the final number of stars will blow up. You can go with an approximation algorithm, and then you have the issues that you have seen before. You have over approximation, but in this case, if one star is input, then also one star is out. So you don't blow up the number of stars that represent your output set. But of course, you can get over approximation errors. So our PyNever supports both approaches, the complete analysis and the approximated analysis, and it also supports an intermediate version. So in the original methodology that was implemented in other tools like Neural Network Verifier, NNV, you can either apply the complete or over approximate algorithm to the whole network. In our methodology, we try to apply an heuristic that chooses dynamically between over approximate and complete algorithm. And the idea is to resort to the complete algorithm only when the over approximation is too coarse to provide the useful results. The goal is to get to something that is less computationally expensive than the complete approximation, the complete analysis, but it is more precise than the standard over approximation. And right now, this is the main novel contribution inside PyNever. There are, of course, other things to PyNever that are written in the paper, the architecture and so on and so forth, but I won't enter into the detail of those, because those are more interesting from a software engineering perspective rather than a scientific one. Okay, so our refinement heuristic is approximately this. So when a star set theta is input to say a ReLU layer, for each variable and neuron, we compute a rank as the difference between the upper bound and the lower bound. If the lower bound is greater than or equal to 0, then it means that the neuron is stable. If the upper bound is less than or equal to 0, then again the neuron is stable, so the rank is 0. So we don't need to perform over approximation, because we won't split the star. Otherwise, the rank is the difference between the upper bound and the lower bound. And the rank is taken as a measure for the loss of precision of the over approximation. And now we are going to refine the variables or neurons with the greatest rank value. Okay, so the idea is that the higher the rank, the more the chance to be refined. This is the current refinement heuristic that we have. And we tried this heuristic on some set of example coming from the well-known Akaksu benchmark. The Akaksu benchmark is about suggesting to a known ship some evasive maneuvers when an intruder enters the aerial space of the own ship. The networks that we are dealing with are fully connected neural networks with 5 stages, if I remember correctly, of 5 neurons, of 50, 5 stages with 50 neurons each. They have 5 inputs, 5 outputs, and there are 6 hidden layers. And they are a well-known benchmarks for networks and properties. So in the case of the Akaksu benchmarks, we are able to deal with all the properties using abstraction, but there are some properties for which over-approximation fails to verify the property. So these are the cases, the properties, and the networks for which we fail to verify the network using over-approximation only. We can check these cases with a complete analysis. And here you can see that the property can be verified with this time in seconds, okay? But if we apply our mixed heuristic, so if we merge between complete analysis and over-approximate analysis, we are still able to verify the property, but we get a dramatic reduction in runtime. So the whole point is that by mixing the two, so by trying to abstract only what is necessary, we can get better runtimes. And as it is shown in the paper, these runtimes are comparable to other state-of-the-art tools, or at least were comparable at the time we wrote the paper, making the approach competitive with respect to the others. We didn't manage to participate in the yearly neural network competition this year. We will try to join in next year, so we'll see whether our ideas plus some additional improvements that we made to Pineapple really stand a chance with other state-of-the-art tools. And in particular, this is what we are working on right now. We are considering, we are trying to work on counterexample extraction and how to use the counterexample in order to drive our refinement heuristic. We would also like to enhance scalability. In particular, right now, we are limited by the way we compute upper and lower bounds for each stage of the network, for each neuron, because we need to solve some linear programming problems, which tend to scale not very well when it comes to dealing with large neural networks. We are going to consider new use cases coming from application, and specifically we are considering controllers for a turtlebot plus a robotic arm and drone, and also a case study coming from the automotive sector about an automated cruise control. And also we would like to add support for closed loop neural controllers in Pineapple, which are by far the application that we believe will benefit more from this kind of techniques. Okay, and this is it. Thank you very much for your attention. And if you have any questions, I'll be happy to answer.
Okay, thank you, Amanda, for the interesting talk. We have about 10 minutes. Take some questions. Please, let me know if you want to ask some questions. Any questions? No?
Okay, so we are 10 minutes earlier.
Yeah, so we have 10 more minutes, and I think we start next talk precisely on time. So if people wants to join on time and interesting one particular talk, they can just cut in at the half past time or 1 hour time and to listen to that talk. So that's our strategy. Yeah, I'm not the area of neural network, but I'm quite fascinated about the results where you can teach about the abstract models, so that to improve the position of the outcome of neural network, which is very interesting and to me. Yeah.
Okay, so I'll be waiting if there is any question that pops out before the next talk begins.
Okay, yeah. Thank you very much.
Thank you very much.
I think we have a question from the audience.
Yeah, from Ariel. Yeah. Please feel free to ask.
Hi. Since there are no questions being asked, because I'm also not quite an expert in this area, I was wondering if you can talk more about what is the space of current tools and how does PyNever fits into that space? Is it different between the tools engineering, or is there some more fundamental differences?
Okay, so essentially, PyNever, thanks for the question. So essentially, PyNever is a hybrid between two tools that were already out there. And one is Neural Network Verifier by Vanderbilt, essentially by a group of scientists at Vanderbilt. And NNV was the only tool that I know of to use star set abstraction. And the other tool that we got inspiration from is ERAN from ETH Zurich, which again, since the onset uses substrate interpretation in order to solve problems. So in fact, our tool is strongly inspired by these two. And right now, the way it fits is that ERAN and NNV both feature over-approximated and complete analysis. In the case of NNV, there is no possibility to mix the two. So NNV is at least the version we were comparing with. I don't know if there have been recent development, but NNV lets you analyze a network either with the complete approach or with the over-approximated approach for the whole network. We can mix and match. So this is the main difference between us and NNV. And with respect to ERAN also features a complete analysis, which is based on mixed integer programming. So the way we deal with a complete analysis is different from ERAN and more similar to that of NNV. And right now we are building into PyNever some capabilities that, to the best of my knowledge, are not built in neither in ERAN nor in NNV. Plus, PyNever as a library supports also learning through an interface with PyTorch. So the idea is that PyNever and the tool that we are building on top of PyNever, which is going to provide also a graphical user interface, will let you also build a neural network and learn from a data set. So the idea is that we are trying to come up with some sort of integrated development environment for neural network, where you can sketch your neural network, learn weights for the connections, and then verify it, and possibly in the future repair it. So it's an ongoing project, which you are just looking at the initial stages.
Thank you. So does it mean that you have NNV and RN as dependencies, or do you re-implement all the algorithms?
No. We do not depend on NNV or Iran. We depend on PyTorch for the learning part and Google optimization suite for the computation of the star sets. So we have some dependencies, but not with respect to other verification tools right now.
And so you don't depend on MATLAB or something. Like I remember NNV, I think, was dependent on MATLAB.
No, we don't depend on MATLAB.
Oh, that's very nice. Thank you.
You're welcome.
And I'll let others ask questions, but if not, I'll ask another one.
Yeah, if there are any other questions, or you can continue with your question if you if there are no others.
Are you planning to also attack recurrent neural networks, or just I don't know what the other ones are called?
Not in the near future, because we are still working on getting more sizable results. I mean, we are still trying to get to deal with feed-forward neural networks that are closer to the ones that are actually used in practice. But in perspective, yes, recurrent neural networks might be a kind of network that we would like to deal with, but definitely not in the near future.
I see. Thank you. Yeah, I'm coming from a verification community, and it's interesting to see how, or like what you're doing to me, that kind of sounds like BMC, and then recurrent neural networks kind of look like transition systems where you would need invariants or something like this. And it's interesting to see how the techniques morph.
Yeah, the approaches I've seen that deal with recurrent neural networks perform some kind of unrolling of their functions and then verify them up to a certain depth. So in fact, what I've seen around looks very close to what is done in BMC. And I mean, in principle, you could do that. I mean, if you enroll a recurrent neural network up to a certain depth, then you get a large feed-forward network that you can then check with any tool that deals with feed-forward networks. In principle, this is already doable also with PyNever. In practice, the size of the enrolled network might be out of our reach and out of the reach of many other tools that are out there.
But this network is likely to exhibit symmetry. And so what happens in BMC is that the symmetry is exploited. You can infer invariant, so you can, what you learn on one cycle, you propagate to another cycle.
Of course,
and so there's maybe a way to tame it.
You can clearly, I mean, all those three, I mean, in the end, the neural network is just a software, right? So all the tricks that have been known and applied for a few years now in the software or hardware verification community can carry over to neural networks as well.
Okay, yes, thank you very much. Please join me to thank our speaker again, Anando, for the interesting presentation. Okay, we about to move to the second talk. I suppose the next speaker will be prepared. So it's a talk on the paper verifying verified code.
Yeah.
Yes, okay. So are you able to share your screen?
Yeah, I'm just starting right now. Just a minute.
Okay, that's good.
Sorry,
Matthias,
there is just a moment. Let me try again. I can't. Zoom is not letting me share that particular window. I'll just
okay.
try again. Just
Okay.
give me a minute.
Try again. I think you have the right to share. Okay. All right. Yeah, we see the screen. All right. You may start your presentation. You know, it's all yours. I think you might be. Oh yeah, that's all right. You're not muted. Okay.
Siddharth, can you say something? I can't hear you.
Yeah. I can't hear as well, so I'm not sure whether there's a speaker problem from your side or not, because we can't hear your presentation. We can see the screen. Yeah. I think we hear us now.
Can you hear me now?
Yes. It's all loud and clear.
Okay. Yeah.
Yeah, please go ahead.
Okay. So the paper I'll be talking about today is verifying verified code, and it's joint. The team members are from the University of Waterloo and the Technion. So I'll introduce the team first. On the top left it's me, Siddharth. Then we have Jiang Zhu, Yusin Su. In the bottom row, we have Professor Yakir Vizen, Dr. Yuan Bao, and Professor Ari Garfinkel. Now, the crux of our case study is based on the original case study on AWS Common Library. And this was published at ICSI 2020 by Chong et al. And AWS Common is a library from Amazon Web Services. It is a cross-platform C library which deals with low-level data structures. Now, the library itself is self-contained and it's written in C. And what is interesting is that it has been verified thoroughly using a bounded model checking tool called CBMC. And it has more than 160 unit proofs for different functionality of the library. Now, more importantly, the library is open source. And so, and the proofs are, as part of that, are also open source. So it allows us to build and recreate some of the findings or the whole system that that the original paper used. This is where we go into our case study. But before that, we'll introduce some concepts that are needed for this talk. So the essence of how verification tasks are structured in the AWS Common Library is code as spec or CAS. Now, there are three salient features of this. So first, the specification is written as code, in the same code that the actual program under verification is written in. Secondly, the structure of the verification task is in the form of a unit proof, which is similar to a unit test. And third, we extend the programming language with some primitives which help us deal with expressing verification intent. So things like assume, assert, and non-determinism. So let's look at this example in detail. This is a unit proof in the main function. The part in green is the function we want to verify. This is a function which returns the capacity of some given list. And the first thing we do in this function is initialize the function, initialize the list. And then we set up some preconditions. And you can see we use the assume keyword. And in green, we call the function under verification. And finally, the post conditions are given in yellow. And you can see we use the assert keyword. Now, just to reiterate, code as specification has three main aspects. One is we use code to write specifications, which is the pre and post conditions. And the most important thing that it allows to happen is that it empowers programmers without verification background to contribute to verification in terms of writing proofs and maintaining proofs. Now, to enable that, the unit proof is structured like a unit test. So it is familiar to anybody who has worked in a test-driven environment. And third, the programming language, in this case C, is extended with some minimal things to express verification intent. So things for symbolic input, assumes to specify preconditions, and asserts to specify statically checked post conditions. Now, the original study propelled us to ask three research questions. The first is, while CAS was enabled using a particular bounded model checking tool CBMC, we asked if we could actually use CAS across multiple analysis tools, because in the end, the specifications as code allowed in principle for us to adapt it. And the answer we got was, yes, we can do it, but there are caveats. And semantics are semantics of the code, of how that code is interpreted by the tool, is very important. And we need to design specifications with multiple tools in mind from the beginning. Secondly, we asked the question, are there bugs in code which has already been verified? And the answer is, there are no bugs in production code, but we did find bugs in specifications, and some of them were serious bugs. And today they don't hide any production bugs, but they could have, or could in the future. Now, the third question we asked was, can the specifications themselves be improved? Because the specifications are now code. So can we use our experience in both specifications and writing code to improve them? So the answer is, CAS by itself doesn't make specification writing effective specifications any easier. But through experience, we can make certain specifications more efficient for the tool, and also easier to read. But it's a trade-off in some cases. One specific trick that we can use is to have built-ins which make expressing certain intent very compact. So for example, we had an isDref built-in, which was used before any access to memory, read or write access, and that helped us through an error or through an assertion error when we were out of bounds with respect to the object we were accessing. Now, going on to the first research question, does CAS empower multiple analysis tools? So I've already given you a hint of what the story is, but I'll go into depth. Now, the promise of CAS is really great, because what it says is that the specifications can now be written and maintained by non-verification experts, because it is in a language they are comfortable and intimately familiar with, which is their programming language, which the the function under verification or the code under verification is written in. But an important question is, what is the semantics of CAS? Now, CAS is written in C, and the semantics of C has been a vexed question for a long time. And really, there are three ways of looking at semantics of C. So the first semantics of C is the one which is specified by the ISO C standard, that is the official C semantics. The second is the semantics that is implemented or designed into tools. So the tools can be analysis tools, or the tools can be compilers, either exotic compilers or mainstream compilers. And the third is the semantics that a developer understands through their hard-won experience by working through mainstream compilers or in certain contexts. As an example of the discrepancy, a pointer comparison between two differently allocated objects is undefined per ISO C standard, but compilers support this in a consistent way. They allow this, and programmers widely use this and understand that pointer comparison is something that works in mainstream compilers. Now, why should we care about the semantics of C? We are talking about CAS here. So in CAS, tools may interpret code one way. So for example, your verification tool may interpret code in a certain way. The developer understanding may diverge with how the tool interprets CAS. Developers are familiar with what we call de facto semantics. De facto semantics are those semantics which are implemented uniformly across mainstream compilers and understood consistently by developers. Third, the production compiler itself might diverge with the verification tool interpretation. And this means that my verification or analysis tools can miss bugs. So this is why semantics of C or this question becomes very important. Now, to tie off the discussion, what is the right semantics to use for verification tools? We argue that de facto semantics, which aligns with developer understanding, is the right way to go. In practice, it is followed by many tools. And so once we have written specifications with de facto semantics, we get to use or execute our semantics on these other tools which follow them. And finally, because we are now closer in meaning to the code that will be executed, it leads to stronger guarantees about code. So our one argument is that using de facto semantics is really needed to fully realize the promise of CAS, and it makes verification more practical and approachable by developers. So I'll show an example here. So this is a CBMC unit proof from the original study, and here functionally we are checking if we are getting an element from a list, and we are asserting some post conditions on that. The functionality is not of consequence here, but how the code is structured is. So before we get an element from a list, we have to create a list. Now in CBMC, if we create a uninitialized variable, then it is treated as non-deterministic. So in lines 2 and 3, we create a list L, and then we have certain assumptions on this. And this is understood perfectly by CBMC. But if the list is bounded function actually reads L before writing to it, then it is undefined behavior in C. And so to a developer who is well versed in C semantics, this might come as a surprise. And so this is a discrepancy or a divergence between de facto and tool semantics in the case of CBMC. Similarly, here index is not initialized and it is treated non-deterministically by the CBMC tool. And again, the same problem arises. Now, there is good reason why CBMC and some verification tools treat uninitialized variables as non-deterministic. It really eases the task of verification because one only needs to specify what one intends to verify, and the other aspects of the code are left unspecified. And one, this helps proof writing, and secondly, it can also help verification become more efficient because there are less constraints to worry about. Now, in the case of Seahorn, which is a tool we developed, we cannot use the specification on the left because Seahorn uses de facto semantics. It is part of the LLVM compiler. It uses the LLVM compiler toolchain. And the way we get over this issue is actually quite simple. So to make the code on the left valid C code, we in lines 2 and 3 on the right, we have to call a explicit initialization of the list L, which initializes the list L in a non-deterministic manner. And this is the memhavoc function which we've created. Similarly, on line 7, instead of leaving index uninitialized, we initialize it by returning by using a value from a non-deterministic function, which is nd size t. Now these small modifications makes the code very friendly, or rather it follows de facto semantics. Now the added advantage of this is that once we make it conform to de facto semantics, we can then apply another class of tools to the same proof. So we have applied a tool called libfuzzer, which is a fuzzing framework. And this actually executes the proof on a real machine. And so we get this for free by moving to de facto semantics. Now, another aspect of looking at multiple tools is that tools have different ways of initializing. We looked at one way of initialization. Now, Seahorn and libfuzzer also have different ways of initializing. So here on the left in Seahorn, we want to initialize len and cap, two variables. And the way we do it is how we do it in a normal verification tool is that we non-deterministically have non-deterministic values for len and cap, and then we constrain it using assume. But in the case of libfuzzer on the right, this is a very inefficient strategy because libfuzzer generates a random value in each execution, And if we just say that a random value has to be within some constraints, then that whole execution is wasted. So instead of wasting that execution, in lines 5 and 6 in libfuzzer, we actually massage the whatever random seed or random value we have gotten to be within the range we want. Now, this might seem like it would break CAS because you have two tools totally different and you can't even share a basic spec. But because specifications are written as code, we can actually use normal established refactoring techniques. So we can put the tool specific initialization in a function. So on the left, we put it in a C init buff function, and the right, I put it in a fuzz init buff function. And then when I compile for either chorn or libfuzz, I can choose what to link in. So the strength of CAS is that once specifications are code, then I can actually use refactoring and software engineering tools to get over these differences in how tools work. Now, a question is, are there bugs in verified code? And as to reiterate, we did not find bugs in production code, but we found bugs in specifications. Now, this is a bug in a representation invariant for the AWS bytebuf data structure. A representation invariant for a data structure is a predicate which is always true of the data structure before any operation and after any operation or every operation. Now here, the original assertion was that memory inside a buffer is writable till the length of the buffer. But actually, the assertion should be that the memory is writable till the capacity of the buffer, which is at least its length, but it can be more than its length. Now, this bug was subtle enough to be preserved by each function, and so it was never caught by it didn't actually hide any production bug. Now, we have found other bugs, and the question arises on if how did we find this bug? And interestingly, the process of finding this bug is ad hoc. In the interest of time, I will not go through it. But we have developed some tools, or at least one tool, to help us sanity check specifications. So vacuity detection is a sanity check that is well known from temporal model checking. It is also known as antecedent failure. It basically says that a property is satisfied vacuously if it is true, and at the same time a stronger property is also true. But a question arises on what is a property in CAS, because specifications are code, and what is vacuity in the case of CAS. So our definition is that a property is an assert of the form if A then B, and it is satisfied vacuously if and only if it is never reachable in any execution. Now, one difference between vacuity and code coverage, which was used in the original study, is that vacuity detection is actionable. Like there is a failure in verification when vacuity fails, but code coverage is has a qualitative report, and there is noise. And so the bugs we found were also found by code coverage, but they were not acted upon because there was a lot of noise for other issues. So I will skip this section. I will go straight to experiment. Here we see that even using de facto semantics with Seahorn does not cause a slowdown. So Seahorn remains a order of magnitude faster in overall times. But we don't want to spend too much time on head-to-head comparison, because each tool is slightly different in how it encodes properties. Specifically for CLE, we force it to enumerate all values rather than pick up specific one. So you see that it's slow, but at least we have meaningful comparison with Seahorn and CBMC. And so one question that we would like to address is why we don't use the AWS C common benchmark that is present in SVComp. So our goal with Verify C common, which is our project, is different from that of SVComp. So we really want to study applicability of BMC in developer context. And SVComp pre-processes the AWS C common functions along with the proofs. So it's just one big C file, and it loses some of the nuance that we need for our analysis. And for example, it does not have a unit proof code structure. It only uses the CBMC unit proof, which we cannot use as is. And it has no build system, so there is no easy way to mix and match tools and proof artifacts. Now, as part of this study, we have we have a artifact in terms of a continuous verification environment, where each night we run a plethora of tools against the latest AWS C common code. And you can see on the bottom left, we have a continuous integration pipeline. It's all green in this case, but and we also have open sourced our entire study, all our proofs, in the spirit of the original study. Now, our conclusion is that CAS is practical and scalable approach for specifications, but using de facto compiler semantics in CAS enables many verification tools. Secondly, debugging bugs in specifications is an open problem. We show some ways to do it, like vacuity detection, but it's not perfect, and there are challenges even in our implementation. And third, specifications can be written in multiple ways. I didn't have time to cover this, but I can speak to it later if needed. Our future work is that we want to add more verification tools to our continuous verification pipeline. And if you would like your tool to be added, please talk to us. We are very interested. We are also very interested in studying other industrial software and seeing how we can apply our techniques or any verification techniques to them. This includes code in other languages like Rust and C++. So please again talk to us if you have a proposal for us. And finally, we want to continue improving the Seahorn BMC engine through these case studies. And we want to ultimately move beyond validating tools using isolated benchmarks to practical software. I think that is it. Thank you.
Thank you for the presentation. I think we have maybe 1 or 2 questions, and because we are slightly running out of time. Are there any questions from the audience? Yes or no? I have a question regarding so it's a good, I mean, I think it's a viable idea to combine. I think the basic idea of a CAS is to combine specification with the programming language, so providing some level of guarantee, and the backend verifier can, as code, I mean, whether it's runtime verification or non-runtime, it can verify the code. Have you compared this approach with some other, like, I mean, from my knowledge a few years ago, there was like Spec Shop, there was JML, which also take the similar approach of inserting like, the specification, part of the specification into the code and provide kind of verification. So have you compared your approach with these other ones?
Yeah, so the short answer is we have not. Also, to clarify, this is an approach from the original case study from AWS, which only deals with the C programming language. And we have kind of taken that idea further and using it on other tools. But yeah, when we're looking at other languages like Rust and C++, I think we will need these ideas because those languages don't have data, like they have data hiding and visibility issues, which I think are dealt with more fully in JML. At least that's what I know of. But yeah, we have not currently looked at that.
So when you, when on the feature work slide, you said, you are interested in integrating other verification tools into your framework. So I would say, how difficult would it be to integrate another verifier into your framework in supporting a specific language, and that can be used on the code itself?
So if you're talking about a verification tool that works with C and de facto semantics, then it is quite easy. So in fact, after the work on our paper, we have added the SMAC bounded model checker, which also works on LLVM bitcode. It is similar to Chon. And for us, it was quite easy to add it. Like we had to not change any of the proofs. But yes, if we have to add a new language, then I think it is considerable work. We would need like our tools to understand that. But also we have a CMake build system that is not tied to a particular library or language. So in fact, that itself is something that can be used either by us or by other people to build a continuous verification pipeline in any language or using other verification tools.
Okay, I think we can conclude for the presentation, second presentation. Please join me to thank our speaker again. It's very interesting work. Thank you.
Thank you.
We're gonna straight move on to our third talk, which is will be on verification by gambling on program slices. I believe the speaker will be Murat.
Yeah, I'm here.
Okay, great. So are you able to share the screen?
Just give me 1 second. Can you see my screen fine?
Yes, we can see your screen and hear your voice. Okay, so please go ahead.
So hello everyone. My name is Murad. Today I'll be presenting work with Federico Mora, Nick Feng, Vincent Hui, and Marsha Chechek, and its on verification by gambling on program slices. So the problem that we're trying to tackle is, I'm sure very familiar to everyone, is that automated software verification is very expensive, and it's often desirable to verify properties in very large programs, but many state-of-the-art verifiers struggle when presented with large and complex code. One of the reasons for this is when you have a program and let's say there's an assertion in that program, the relevant context to actually check that assertion is often much smaller than the entire program. But presenting the checker with the entire program makes the challenge considerably more difficult. So essentially, irrelevant context can massively increase cost. And the question we want to ask is whether we can quickly verify these properties by looking at and considering the program in smaller pieces. So the issue we face here is that manually partitioning a program into correctly small pieces for the verifier to handle can be a very time-consuming and tedious process. The relevant context for particular assertions can be overlapping, and there could be lots of different assertions and lots of ways to split the program. Also, splitting a program into too small of a pieces can also lead to potential false positives due to essential lack of relevant context to prove the assertion. So traditionally, this problem has been tackled through regular slicing techniques, but they can often be too cautious. For example, just taking a backward slice from a specific assertion, or they can be too aggressive, and in that case they may sacrifice soundness. So today I'll present our tool Kick, which takes a gamble and it tries to verify assertions with less context separately and concurrently. So now let's look at a small motivating example. So this is an expert of code taken from about a 550 line program, which is taken from BusyBox. It's an encryption function. And let's say here we want to verify the safety of upper bounds of accesses of these arrays. So to prove that the accesses of these arrays are safe, you don't need any of the information in red, and most of it can be ignored. So that's including most of the 450 lines of code. But when you present this assertions for these properties and the entire program to some state-of-the-art program checkers, they'll struggle to come up with an answer to this seemingly simple task. So and the reason why these checkers often don't work is that they produce very large and complex models that can be difficult for the underlying solver to reason with, and also like modeling the modeling the program itself can also be a fairly time consuming and memory consuming task. And of course, having a lot of relevant context and just having a larger program can make the challenge much, much worse. So our toolkit enables two existing state-of-the-art checkers to solve this motivating example from earlier in under a minute, when they would be otherwise unable to terminate in 2 hours. So some background necessary to understand our approach. So given a specific control flow graph of a program where we say nodes are locations and then squares and arrows represent operations in the code, so these would correspond to lines of code. And in this particular program, we have a single nested cycle, so it would correspond to a nested loop in a typical sequential program. And squares at the end represent terminal locations in the program. A program can have what we call regions, and they're contiguous portions of control flow graphs which have a single entry and a single exit. Here I highlighted 3, but the program can have many different regions, and they can of course be overlapping and extend further. When talking about program safety, we say that a program is safe if no error location is reachable. So for if some reason this 10 is error location and it's unreachable, it could be because we, for example, know that function f never returns a value lower than 0. We also extend this definition to regions, and we say a particular region is safe if no error location is reachable within that region. From that, we can deduce that if an error location is not reachable in a region that contains it, it's also unreachable in the entire program. And from this, we get a key theorem for our approach is that if every assertion is contained in a some safe region, then the program is safe. And we prove this theorem in our paper. So our approach focuses on minimizing irrelevant context so that we can expedite verification. So for this particular would be assertion or like error location, we would pick the smallest possible or the smallest region that we would consider viable and try to verify on that. And this is essentially a gamble because we don't know if proving in that region is sufficient. And it may very well be that we would, the location is actually unreachable, but within the context of this region, it's reachable. And in that case, we say that our gamble fails, so the gamble did not pay off. And we would grow the context and try with a larger region. And then we would continue gambling until more and more context is used. And at the end, if necessary, we would try with the entire program. For that, we define as a shorthand concepts of kick hits and kick misses, and we say that our tool kick hits when an identified region that the tool selected can be verified successfully in isolation, so by itself. In that case, the gamble pays off. So the smaller region that we picked can be verified without looking at the wider program. We also say that kick misses when more context is needed to prove a particular assertion in the region. In that case, we'll have to expand the region and do it again. In that case, the gamble did not pay off and we essentially lost. So it would be way too expensive to choose every single possible permutation of regions in a program. So as a heuristic, Kick currently relies on bodies of cyclic regions. So if we identify a cycle in a program, we would essentially ignore the loop head and then try to um, on the head of the entry node of the cycle and try to verify the inner body in isolation before growing onto the next containing cycle. We also do the same thing with procedures. So the key hypothesis here is that we believe that misses will be cheap and we believe that hits will be very beneficial. The reason for that is why we believe misses will be cheap is because when kick misses, that means the region was essentially too small to check the assertion. And checking a smaller region is usually much faster because you don't have to look at a lot of context and checking the entire program. Therefore, we believe that checking a few small regions should be a relatively cheap gamble. So the workflow of our tool consists of two major components. First, the front end, which contains the algorithm that identifies these cyclic regions and also generates what we call a region nesting tree, which I'll discuss in the next slide. So essentially, the C program with assertion is fed into this portion of our workflow. After this nesting tree is generated, we're ready to pass it on to our gambling algorithm, which would interface with an external verification tool, and it would continuously pass regions to it. It would gamble by passing regions to it. And if it happens to miss, it would go back and then do it again. So what is a region nesting tree? So given that a CFA, a control flow of a program that I showed earlier, we would first identify all strongly connected components, and then here the everything in blue and pink together would be a strongly connected component. But to identify nesting, we would remove the root and essentially run this over and over again recursively until we come up with a tree which is generated from the stack of that algorithm. In this case, since there's only one loop that's nested, it's essentially a line, but if there would be multiple loops in the program, it would look like a proper tree. So once we have the region nesting tree, we're ready to gamble on it. And essentially the way gambling works is climbing the tree, the region nesting tree. To do that, we first identify deepest region for every single assertion in the program. And this would also be the smallest region that contains every single assertion. Well, the region we identified, not the possible region, not any possible region. Then we create a checker process for every region that we identified, and they can of course be run concurrently in this case. Once that is done, we check if the region is safe. If the underlying checker terminated and says that the region is safe, that means kick hit and we're done. And we can actually terminate that process and mark the assertion as verified. This also means that we can more easily obtain partial results for particular assertions. If the region is not safe, that means that we missed. And in that case, we will have to fetch all the parent regions and then do it again, unless we're of course already at the root region. In that case, we would terminate completely. So we implemented our algorithm, essentially the identification and tree generation algorithm in OCaml as plugins for C intermediate language, which allowed us to easily model the control flow graph and identify the segments we're interested. We also implement procedure extraction and all the program manipulation we needed to do as part of this front end. The actual gambling algorithm, which includes RNT traversal and all the interfaces with external verification tools were implemented in TypeScript. And the reason we use the web language for this is because it has a very easy model of dealing with a lot of asynchronous processes and managing them. So we do not support regions with multiple entries and also recursion in our implementation. Not just any regions with multiple entries, but the regions we identify. So essentially cycles with multiple entry points. We then conducted an evaluation with two existing verifiers. First, we focused on CBMC, and this was the main part of our evaluation. CBMC is, as I'm sure many people know, a bounded model checker for C, and we expected Kick to perform very well with CBMC. The reason for this is because bounded model checkers inherently struggle with cycles as they require unrolling them before actually moving to the verification step, which could be a very expensive process which could be a very expensive process. And by shaving off cycles, it could often make it much easier for CBMC to handle a program. We also did a study with Ultimate Automizer, which is an automata-based model checker, which is very different from CBMC. And we chose it for variety, and it is also a top performer in SVComp. We had 3 research questions. First, we wanted to evaluate with CBMC since the heuristic really fits this program checker, and we wanted to see what is the benefit of kick combined with CBMC, essentially when the gamble succeeds, so when the smaller region is sufficient, and what is the additional cost of kick when combined with CBMC when the gamble fails, so essentially when kick misses. And we also wanted to see if does this performance benefit of kick actually extend to other verifiers. So is this technique even useful with other verifiers, keeping the same heuristic in this case of shaving away cycles. And we also wanted to see if kick can scale to large and real world programs, which is essentially the whole point of getting rid of irrelevant context. To answer research questions 1 and 2, we conducted a thorough analysis with synthetically generated programs, and that was done for both CBMC and Ultimate Automizer. As a baseline, we first took 15 SVComp programs that were base benchmarks, and we systematically introduced irrelevant context to them, and we simulated both hits and misses. The reason we just didn't run this on SVComp is because we didn't expect to perform well, because benchmarks for verifiers usually do not have irrelevant context. They have a task and then assertion following that task that essentially proves that the task did what it's expected to do. And this is not what Kick is designed to handle. So we took these as baseline programs or verification tests, and then we synthetically introduced irrelevant context. And we used 10-minute timeouts for all verification runs. So when generating programs synthetically in our systematic analysis, we took six preset program structures that we came up with, which were essentially modeled like this, and some of them guaranteed kick missing, so they were guaranteed for kick to perform badly on, and some or at least worse than CBMC, and 2 guaranteed kick hits. So it was essentially a balance. We also had 1 baseline program structure with no subregions where we expected 2 tools to perform pretty similarly. This was just essentially to measure the additional burden of running of the front end part of kick. And we also had some examples that had a mixture of kick hits and kick misses. There were also bound presets that were varied in every case. So what we found with CBMC is that when combined with Kick, it was able to solve a lot more of our synthetically generated examples. And if you look at this, than CBMC alone, and if you look at this graph here on the left axis, we have the time taken by CBMC. This graph is logarithmic. And then on the right axis, also logarithmic, we have when Kick combined in CBMC, so in milliseconds. So everything below this axis would be a miss. So that means Kick took longer than CBMC to solve, and everything above is a hit. And what we see is that misses are proportionally more impactful on examples under 600 milliseconds. And then essentially, as examples get harder and harder, misses become more or less negligible. This means that the benefit of a hit can be very, very beneficial. And we can see there's lots of hits in higher up in the graph, but the cost of a miss is proportional essentially to the depth or the challenge of the program, and they can be very cheap. We also found similar but less apparent results with UA. UA was still able to solve more examples with Kick than by itself. And we also see that the misses were primarily concentrated in this section of the graph, and there were a few hits as we look at more challenging examples that are quite apparent. And then performance gain, of course, wasn't as large as CBMC, but if we adjust our heuristic to focus more on a specific program checker, then we could see better results with different program checkers. But nevertheless, even with this heuristic, we were able to solve more examples than the checker was able to solve by itself. We identified two threats to validity to the systematic analysis, and that irrelevant context introduced was limited to cycles, which again also affected CBMC a lot more directly than UA, although both checkers can of course be slowed down by irrelevant cycles. All examples are also synthetically generated, but we also varied systematically, and using synthetic examples really allowed us to control for hits and misses and evaluate the cost of those individually, the cost or benefit of those individually. For our research question 3, we conducted a small case study on the motivating example I mentioned earlier, and assertions were manually inserted to check for excesses of upper bounds of arrays. We used 2-hour timeouts and 8 GB memory limits for our case study. So this represents this graph shows the region hierarchy of the program that we evaluated, which is curve 25519. It's taken from BusyBox and Wolf SSL. Here, the white boxes are particular functions that are in that program, and then the blue boxes are regions that were identified as KIC as potential regions to verify in isolation. And here, arrows between regions represent essentially region containment. In blue region segments, these represent lines of code, and white boxes heading and arrows heading to other white boxes are function calls in this case. And 14 assertions were inserted to essentially check for all arrays of static sizes for all upper bound array accesses. So what we found here is that when CBMC and UA were run without kick baseline on this example, the entire 450 line program, and this was all in one file, both checkers were unable to terminate. So CBMC actually ran out of memory in the unwinding stage without getting to the actual verification stage. And Ultimate Optimizer was unable to terminate in 2 hours, and we did not try to giving it more time. When Kik was configured in sequential mode, so without running processes concurrently, we saw that both checkers were actually able to terminate very quickly, both in under a minute, and they found a result for every single assertion that we added. And in concurrent mode, the benefit was also visible, but it was more apparent for tasks that would take more time, which is also what we expected. So essentially what we see is that Kik enabled two existing state-of-the-art program verifiers to terminate very quickly in under a single minute, and on a real example taken from a fairly large code base, which they would otherwise be completely unable to handle. So we also identified two threats to validity to this case study, and of course it was limited to one type of property, array bounds, and one example. However, in systematic analysis, we used lots of different baseline programs with verifying different properties, and this how well we perform on different properties also depends a lot on the underlying program checker, not just our approach. We also did not evaluate frequency of hits and misses in real world programs, and it's essentially unknown now, but we also showed that the cost of a miss is very small. And when we talk about large programs and looking at small segments, they could essentially be negligible when compared to the entire program. But the benefit of hit when looking at the entire, when versus evaluating was the entire program can be very, very large. So to recap, Kik is very useful when trying to verify properties in large programs where limited context is sufficient to prove a particular property. Again, this could be something like safety of array bound accesses. Without Kik, finding sufficiently small regions for this could be a very tedious process. It's of course possible to do it manually, but it would be very time consuming. And as we showed in our evaluation, cost of misses is very small and scales very well and was input, which means gambling is a very cheap process and taking a gamble is cheap. And when Kik hits, it can terminate much faster than the underlying checker, which means benefit of winning a gamble is very, very large. So some related work is, of course, program slicing for verification, which focuses on finding a relevant subset for a particular assertion. And that can also make verification easier. And you could say that Kik essentially acts as a program slicer that specifically exploits locality of some properties. Also, some differential program verifiers, one of them is TooClever, perform very similar cycle extraction or simplification to Kik, but they do not target program safety like Kik, and they do not reason about regions in isolation. In the future, we plan to use a combination of checkers and dynamically choose between different checkers for different regions. That means a single program could be verified by multiple checkers at the same time. We could use different checkers for different pieces or different assertions, depending what's best. We also plan to insert additional facts into extracted regions using static analysis. That would allow us to miss less often and essentially hit more often. This could be something like constant values that could be essentially propagated down in the towards the extracted regions. We also plan to experiment with different heuristics for regions, such as, let's say, isolating expensive function calls or expensive floating point operations that we think might not be entirely necessary. And that could also further reduce the cost of verification. That's it. Thank you very much.
Thank you for the interesting talk. So are there any questions for the speaker? Questions?
So I have a question.
Yeah, go ahead.
Hi. So this is actually from your paper. So I don't know if it was covered in your talk. I'm sorry if I missed it. So you say that Quick covers a subset of C. Is that correct?
Yeah, so for example, some stuff that we do not, I think I mentioned it earlier about the limitations in the implementation section. Some examples, some things that we do not support is, for example, regions with multiple entries and especially cycles. So for example, if you had like a cycle that is generated with a specific configuration of go-to statements, we would not be able to deal with that program. And also if programs aren't reducible, and that essentially would be if you had like a go-to statement in a cycle that wouldn't jump out of the cycle downwards, but essentially would jump upwards from a cycle, which is very rare. It's rare for real programs to be not reducible. That we also can handle. C also has support for recursion, but because of our tree climbing and dealing with procedural algorithms, we presently don't support recursion, but that's more of an implementation limitation. But handling something like mutual recursion, for example, would be quite difficult with our approach. Even if we try to implement it. Yeah. So that's where the subset part comes from.
Hey, Ariel, you have a question? Go ahead.
Yeah. So I wonder if you can comment on how do you deal with computing preconditions for these regions? So for example, what if I have, say, a cycle, and in this cycle I use a pointer? And I need some code before it in order to understand where the pointer points to.
We currently do not deal with this, so it would be, I guess it's insensitive of the context, this analysis. There's some preconditions for particular cycles that we do deal with. For example, if looking at a loop, the precondition of entering a loop would be essentially the exit condition of the loop, and that's an example of a precondition we do deal with. But we do not presently support something like a pointer analysis.
So how would this work? Like CBMC, for example, is very strict at making sure that every memory access is legal. So if you give it a slice which say uses a pointer that wasn't allocated, that will cause it to fail because of that, and then you degenerate to just.
Essentially, if you like extract it as a procedure and then it wasn't allocated.
Well, here you have A, for example. What is the size of an array A, an array B? right? Like they have to be allocated in order to have size. If you just
Right,
extract this.
These are static, essentially static arrays where types are visible, and the extraction algorithm, when you extract it, it evaluates the type where it was declared, and then it will essentially properly set what it was in the program. So it would essentially move it there, what the declaration of the type was and the size of the array was.
Right. But so if their size was dynamic, that wouldn't work, right? Because we would need to extract the mallocs.
Yes, right. So in this study, we did not evaluate dynamic arrays, but I guess you could do it with additional static analysis. Yeah, yeah. And then use more regular slicing techniques in combination in that case. Yeah, but these are not...
One word that comes to mind is by abduction in tool like infer.
Mm-hmm.
But it's not an easy static analysis to do.
Yeah, that's definitely a very good question. Yes, but yeah, these arrays were they were statically defined. They were not dynamically allocated.
I guess another comment that I want to make is that if you look at like real world verification case studies, like the one that was presented right before your talk, I'm sure you're going to find lots of examples where there is lots of irrelevant code, and it's not prepared to just be code and irrelevant assertion. So it would be interesting to see how effective it is in that context.
Yeah, it definitely depends how far the relevant context is for the assertion. Here, it's not very far. So essentially here we would try to look at this line in isolation and then compare J equals I and miss, and then look upwards, and it would be pretty close. And I think for lots of array properties that is true, but it is definitely true that if you look at particular class of safety properties, this wouldn't be very effective because locality can't be just as easily exploited as, let's say, with loop balance, and it could be like further away. That's true.
Well, sometimes data flow can be close even if control is far. So if you follow the data flow chains as opposed to control chains, it may not be that far.
Yeah, that's true. That's also a good point. Yeah, we could do something like that.
All right, thank you.
Thank you.
Thank you for the questions. Are there any other questions? If not, I have a comment or maybe a question regarding the localization of the regions in the program. Would it be regionalization? Because my comment would be, would that be useful for like automated program repair? Because now that you localize or regionalize the verification, would that region be useful in, for example, debugging or repair the code?
It's certainly possible. I actually haven't thought about like this technique from program repair approach at all, but I could see where this could be useful if it's more easier to look at the smaller region or locality, and when essentially the repair or the bug is located. Some other tools that we use in the paper cited, they use when you check like equivalence checking with client libraries, and they were able to and it uses a similar technique there. In that case, maybe combining something like that with program repair or like upgrading libraries. In that case, I could definitely see where locality can be easily exploited.
Okay, yeah. All right, if there's no further questions, we can thank the speaker, and that concludes our section 7 of the program. It's lunchtime break in Brisbane, so it will resume 3 o'clock Brisbane time for the next session. Let me just double check. Yes, section 8 is 3:30. Yeah, so that concludes our session, and thank you very much. Thank you everyone for attending. Okay.
Thank you very much. See you guys in 3.5 hours.